Okay, all right, so let me start by thanking the organizers for inviting me and for putting together this very nice conference, and thank you all for staying. I know it's the end of the day and you're all tired. So today I want to tell you about a story I've been pretty excited about for the past year or so, which has to do with the new class of measurement-induced phase transition that we call charge sharpening transition, and which in turn has to do with learning something pretty simple, not entanglement, but global charges. Okay, so like many other talks this week, this talk is going to be motivated by the advent of the NISQ era, the fact that we have all those amazing experimental platforms that raise new questions about many-body quantum dynamics, and in particular about interactive quantum dynamics, okay? And in particular, the role of the environment and role of the observer. Okay. So in this story, the role of the observer and of measurements will be really crucial. And so the story I'm going to tell you about will rely a lot on this idea of measurement-induced phase transitions that I think we heard a lot about yesterday. So I'm not going to have an intro on this, and I hope that's okay. So just to set the notation, you have those monitored quantum circuits as a function of rate of measurements that are called P. You have this phase transition that, again, you heard a lot about yesterday, that separates volume law and area law scaling as a result of competition between scrambling dynamics and disentangling measurements. So there are a lot of different perspectives on this transition. And again, we heard about this partly yesterday. But the one that's going to be, so the one perspective that will be useful for me today is in terms of the amount of information that the observer is gaining from the measurements. Okay. So in this volume law phase, so at weak measurement rates, the way you can understand that this phase exists is because the quantum dynamics is a very efficient encoder of quantum information. So you're effectively scrambling information and hiding it from the measurements. Okay, and so that's a way you can understand that this phase exists. And so this phase, basically the measurement record is essentially random, so you're not learning about the state. In contrast, in the area law or pure phase, measurements efficiently extract some information about the state. Okay, and so your state at long times is determined by recent gates and measurements. All right, so one thing I should emphasize is like current experimental realizations of this phase, despite this very appealing, perspective that it's about, again, how much you learn about your system, have been limited to relatively small systems. And that's because, the most naive observables you can construct that will probe this transition are nonlinear in the state and require preparing the same trajectory over and over. And that's this post-selection problem that, again, we heard a lot about yesterday. So alternatively, you can phrase this as a decoding problem, which we can do for Clifford gates, but not more generically. Okay. And so there's been a lot of effort to go around this and to go beyond this post-selection barrier using space-time dualities, and some proposals we heard about yesterday that are very recent, either using machine learning to do this decoding problem, using feedback, cross-entropy benchmark, and so on. Okay. So here in this talk, I want to take a very different perspective. I'm going to talk about a different problem, one that is simpler, and my goal will be to predict a simpler observable that is global charge. I'm going to imagine considering a system in which I have a conserved U1 conserved quantity, say particle number or total Z spin, and ask about how much information you gain from your measurements and whether you can learn the charge of your system from local measurements. And I will argue that this process is fundamentally limited by a new type of transition that I'm going to call charge sharpening transition. Okay. So please interrupt me as I go if you have any question. Okay. All right, so the simplest way I can motivate this is by the following game. Okay. So let's imagine, again, you have a system with a U1 conserved quantity. So say particle number or spins, and you conserve the Z components. And let's imagine your initial state is in a superposition of different charge sectors. So here, the ket Q is a scrambled state in charge sector Q. And then you have a system for simplicity, let's say it's a quantum circuit which preserves charge, and you're allowed to monitor the system, and so you have an observer, Eve, who's eavesdropping on the system and is allowed to make some local measurement of charge in random location with some rate p for a time of order L. So Eve is collecting some measurement record of, there was a particle there was no charge there, and so on and so forth, okay? And then Eve's goal is to guess the global charge of the state from that measurement record, okay? And so what you can do is at the end, once you're done, you can, in one shot, measure the charge of your system and see if Eve got it right. Okay, so it's a very well-defined game. And of course, Eve's goal is to make the best guess based on those measurement records. So there are many variants of that game. So here I started with an initial state that's a superposition of charges. You should think that it's going to be, collapsing because of the measurements. You can also imagine that your initial state is in a definite charge state, Q0 or Q1. And Eve's goal is, again, to learn the charge. So she should guess from the measurement record whether your state has charge Q0 or Q1. Yes?
Does Eve allow to make an error and get the charge?
So are you asking if the measurements are perfect, or?
No, sorry. You say Eve
guesses the charge.
So
is that guesses the operator?
No. So let's say in this case, so you have an initial state that has a definite charge, like Q0 or Q1. Let's say it could be L over 2 or half filling or L over 2 plus 1 or something. And Eve's goal, Eve is collecting measurement records. She measures locally there's a charge or not on each qubit. And from that measurement record, she should guess whether the state was at half filling or half filling plus 1. Okay? So that's the rule of the game. Okay? And so one thing you could do, for example, is average all the measurement records, right? So you take the average charge. Okay? That could be one way to, and that's not an optimal one. That's assuming that the measurements are independent, and you can do a lot better. Okay? All right. So what I'm going to argue in this talk is that this very simple problem is fundamentally limited by a transition that I'm going to call charge sharpening transition. That this Eve can actually succeed and learn the charge of the state with 100% success rate above a threshold that I'm going to call P sharp. Okay, so that's my goal here. So in order to do that, I'm going to take a detour and tell you about U1 monitored quantum circuits and tell you about how we understand the phase diagram of those circuits, and then I'll go back to this learning or eavesdropping setup near the end. Okay. Okay, so here's the setup in a bit more detail. I'm going to take, as promised, a circuit with U1 symmetry. So I have this brick wall pattern. Time is vertical here. On each side, I will take a charge qubit, so a qubit that carries this charge degree of freedom. And I will also, for theory purposes, imagine that I have neutral degrees of freedom, so I have a qubit on each side. And my gates have a block diagonal structure, but are otherwise random. So the block diagonal structure conserves the charge of the qubit. Okay. And I will have measurements with some rate P that will measure charge, measure the qubit in the charge basis and the qubit in whatever basis you want. Okay. Okay, what's the motivation to add symmetries? I can kind of try to argue this from at least two different ways. So from the point of view of like phase transitions and critical phenomena, it's pretty natural to add symmetries to this setup of measurement-induced phase transitions. You could imagine you're going to get interesting new phase transitions. From the point of view of scrambling and quantum information, it's also pretty interesting to have a U1 course of quantity because that will give you a hydrodynamic mode. You'll have diffusion of charge. And of course, the way charge is spreading, information about charge is spreading is very different from that of the information, generic quantum information. So the scrambling of hydrodynamic mode and the interplay of symmetry and entanglement growth are like pretty interesting questions. And of course, many people in the audience have been thinking about them. And here specifically, I will ask about how much information about charge can an observer extract from making those local measurements. And if you think about it, at least in a simple way, it's pretty clear that measuring charge is very special. Okay, even if you have independent measurements, let's say you have very sparse measurements. Okay, so you assume they're uncorrelated. The number of measurements you need to reveal charge, to collapse it, is much less than the number of measurements you would need to, say, purify an initially mixed state. Okay, so more precisely, in order to get the charge, if you have independent measurements, you can convince yourself that the number of measurements you need will go as L squared. Okay, and so this follows from just the central limit theorem. If you want to get the charge density up to a resolution 1 over L, so that you can really nail down what charge you have, you want L squared measurements, just from central limit theorem, right? And this is much less than exponential. So it means that even if you go to a depth L here, that should be enough to reveal the charge of the system. Okay. So intuitively, that tells you that the way you extract information about charge is very, it's a lot easier to collapse charge than to purify. And as a result, you might expect that you have a different phase transition. And that's what I'm going to be arguing here today. So that's the phase diagram of those U1 monitored quantum circuits. So this is P, rate of measurement, probability of measurement at each space-time point. You have this entanglement transition that you, again, heard so much about yesterday at PC. And inside the volume law phase, or the scrambling phase, so this is inside the phase where the measurements are very efficient at hiding information. Sorry, the dynamics is very efficient at hiding information from the measurements. You have this charge sharpening transition, which has to do with, again, charge dynamics. And it separates two phases, one that I'm going to call charge fuzzy, and the other one that I'm going to call charge sharp. So in the charge fuzzy phase, quantum superpositions of charge will persist up to long times. And long times here for me will not mean exponential, will actually just be linear in L. Okay. And this linear in L is the same timescale that we had from central limit theorem. On the other hand, if you go beyond this threshold, the measurements are very efficient at collapsing charge superpositions, and they collapse in a timescale that's not order 1, but almost logarithmic. And if you go to a steady state, if you wait a long time and look at charge correlations, average over trajectories, I will argue that you have some interesting behavior. In particular, this phase kind of looks like a gapless phase. All right, any questions so far? Yes. I think it's still log L, but I should think about it. I would guess it's still log L. Yeah. Any other question? Okay. So that's the main phase diagram. Let me say a few words about how we know all this. So we don't really have a good way to do numerics here. So I'll show you numerics, but because of this physics cannot be realized in Clifford circuits. So we basically have to stick with hard exact dynamics numerics. So we're limited to pretty small systems. So the reason I'm very confident this phase transition exists and we understand so much about it is actually from theory and from mappings onto statistical mechanics models. Okay. So this is a short talk, and I don't want to go into technical details, but let me just give you the key steps, just so you have some idea of how we know all this. So the steps are as follows. We use replicas. That's because that's intrinsically a nonlinear problem, okay, or a disordered system. So we need copies of the state. And averaging over the Haar gates, so the U1 gates are Haar random, gives us some effective statistical mechanics problem that we heard a little bit about yesterday. So this is by now a relatively standard tool. Once you average over the Haar gates, you generate degrees of freedom, which are permutations of the replicas that are like spins in that StatMech model. And you also generate charges, okay? And that comes from the fact that you have conserved charge here. The next step is a bit more subtle, and that's really key to why we understand all of this, is that those permutations, they have to do with entanglement. Okay, they control the entanglement transition. And since the physics I want to talk about is in the volume law phase, those permutations are basically forming a ferromagnet. And so they are gapped excitations. So in a renormalization group sense, what we want to do is integrate out those permutation degrees of freedom that we expect are kind of inert and get some effective theory for the charge degrees of freedom. Okay, those are like nice fancy words, but we can do this analytically in the regime of large D, where D is the on-site Hilbert space dimension of that Q dit. So this is a technical detail, but that's why I had this neutral degree of freedom. It's kind of a large N limit. If I take D to infinity, we can do this in a controlled way. Okay. All right. So the outcome of this is we get an effective statistical mechanics model for what charge is doing in those monitored quantum circuits. And the nice thing about this statistical mechanics model is that it's classical. We can analyze it using field theory, and we can also simulate it very efficiently, even though the original quantum problem is in a volume law phase. And so this StatMech model ends up being pretty simple. It's known as a symmetric exclusion process. It's basically a bunch of random walkers with hardcore interaction. Okay, so that's maybe a bit intuitive. You have Haar gates, and what charge is doing is kind of diffusing randomly. But of course, it's a disordered problem because the measurements are kind of constraining where your walkers should be or not. So you're kind of pinning, depending on the measurement outcomes, whether or not you should have random walks. And so this is like a disordered symmetric exclusion process. If you think of having like copies of your state, you have a phase transition in that model. If you don't measure too much, your random walks are kind of free. And if you have different copies, they can strongly fluctuate. But in this sharp phase, you kind of pin down those fluctuations between replicas. One thing I should say is that this is a controlled theory. Even though we're taking this large D limit, going away from it only leads to perturbations that will not modify the universality class of this phase transition. Okay, so once we have this, it's becoming pretty standard because it's a StatMech model. It's a lot easier than the problem we started with, and we know how to study those. And the way we do this is we map it to some Hamiltonian problem, which has nothing to do with the original quantum system, and then we study low energy physics using standard field theory tools. So I'm not going to go into any of the details. If you're interested, you can ask me. So we get some effective action, which is some replica space for the low energy physics of this problem. None of the details really matter. The main thing I want to convey here is that we have a very good understanding of that transition. It's entirely under control. We can start from microscopics and fully derive something like a field theory for what describes this transition. So we understand this transition a lot more than the entanglement transition. At least I do. Okay. We understand very little about the theory of the entanglement transition, whereas for this one, I claim it's the full theory here. So the main prediction is that you have a transition, which again has to do with charge. And in this effective field theory, you end up generating relativistic Z equals 1 bosonic modes. So basically XY models. So this leads to a Carstelis-Thales universality class. Okay, so you'll have a transition in that model due to vortices. There are some subtleties due to replica structure that I don't want to get into. Okay. But from there, we get a bunch of predictions that we can check and that we expect should hold for this transition. So again, I just want to convey that we understand it very well and everything checks out. So this is numerics. This is actually numerics in that StatMech model. Okay. So we can do pretty big systems because we can simulate that StatMech model using TBD. Whereas again, the original problem is in the volume law phase. So what does that predict? For example, if you look at charge fluctuations, so you run your system for a while, and you look at just the 2-point function of spin or charge, and you average this over trajectories. So this is a non-trivial quantity, actually, because of the second term, right? So the first one is linear in the state, in the density matrix. This is actually the non-trivial part. This quantity has, from the field theory, has a power law behavior. It looks like a Luttinger liquid, basically. So you have 1 over x squared power law in the fuzzy phase, where it looks like a gapped disordered state on the sharp side. This also predicts that if you look at fluctuation of charge between quantum trajectories, this should scale logarithmically with the size of the system you take. And there's a prefactor, which is like a superfluid stiffness, if you want. Okay. So all of this checks out numerically. One of the hallmarks of KT physics, BKT physics, is you can have continuously varying exponents. This is something we can have it here too. The operator the observable that does this is non-local. It's like look at charge parity in some interval, so product of sigma x, and then like square it so that it's not trivial and average of the trajectories. And this will have continuously varying exponents. And again, it works very well. And at the end of the day, everything we can predict from the effective field theory, we can verify numerically, and it all works out very well. So for example, we can extract this superfluid stiffness from different observables and agree very well. This is a threshold where we think we have vortices that will destabilize the state. In this phase, charge fluctuations decay with an exponent very close to 2, as predicted from the field theory. So this is this charge sharpening transition. Everything here is within this StatMech model. Okay, so you have then to trust that all of this will actually work for like a monitored quantum circuits with qubits only. Right? So this was derived in this large D limit. Okay? But we understand it very well, and we have very good reasons to believe that, again, going back to qubits, for example, will not modify the universality class. So this is a lot harder to check numerically, because we limit it to about 20 qubits, right, when we do numerics. And KT physics is very hard to see, okay, especially on 20 qubits. But what we can do numerically is at least show that there are two distinct transitions, one related to charge sharpening and the other one related to entanglement. And the way we do this is by using this ancilla probe of Michael and David Hughes. We couple an ancilla either to two different charge sectors or like within the same charge sector, and we look at the purification of that ancilla, and we see two different phase transitions. The caveat here is we're using simple-minded single parameter scaling, which, if you know KT physics, you should not do. But again, we only have like 20 qubits or so, so we cannot really probe KT physics very well here. Okay, so maybe I should pause, see if there's any question. No, go back to this game or eavesdropping setup. Yes.
So, for usual KT physics, if you're sticking with small systems, right, we know that transient flow is the level crossing, charge state. Is there any analog work setup like that, or is that
Not that I can think of. I cannot think of any analog here, but maybe I should think more about it. Yeah, I should say like that numerics that I showed you. So this one, when we actually did this, we had no idea the transition would be KT. So like in order, we probed this numerically first and then came up with the field theory. So now it would be kind of interesting to revisit the numerics. So that's why we did this single parameter, scaling collapse. Maybe it would be interesting to revisit a bit this numerics now that we have, better theory handle. Yes.
Romain, do you have some intuition about why this entanglement transition of 1/d correction is relevant, but for charge sharpening is irrelevant?
Yeah, so it's a very good question. So I'll repeat the question. So we have those two transitions, the entanglement transition and the charge sharpening transition. And I'm claiming that for the charge sharpening transition, we can go to this large D limits and having neutral degrees of freedom, but that the 1/d corrections are irrelevant. But for the entanglement transition, you can also take that limit. And when you do that, you get classical percolation. And for the entanglement transition, we know that those percolation is not the end of the story. And we know this analytically, like the 1/d corrections are a relevant perturbation at this percolation fixed point. So we can show this analytically here. So the reason I believe that for the charge sharpening transition this is not the case is the argument I gave on that slide. So the reason is like the only thing we threw away by going to that limit are those permutation degrees of freedom. And intuitively, they are, again, so this is not an entirely rigorous argument, but in that regime, you would expect you just have a ferromagnet, and your permutations are just gapped. And so in an RG sense, what you want to do is, again, integrate them out. Doing this in practice is something we can only do in a large G limit, but from, if you believe just general RG, the general RG philosophy, you would believe that it would be perfectly fine, right, to do this. Like this, yeah. Yeah, either way. Good.
Here, maybe continuing on that question, is it here actually that in this case, in presence of charge conservation, it's still in the large P limit, same transition and
Oh, the entanglement transition? No, I actually think it's different. It's very likely a different universality class. I still believe those permutations are probably gapped and fine here, but so you're asking if the entanglement transition could be different. I believe it's going to be different. I think it's going to be different. We don't have a good theory handle on this, but I would believe it's going to be different, just on different symmetry. And in fact, I think Jed Pixley's group is working actively on measuring new exponents, and I think they're seeing some differences from numerics.
How stable to which breaking units you want to
No, I really need U1. So you can ask, if maybe you go to the end and things like this, but I don't want any U1 breaking error. I really want to, yeah, it's really crucial to my story that you conserve charge. The measurements conserve charge as well. Okay, so to wrap up this talk, let me go back to this, so this was field theory and convincing you we understand that phase transition very well. Let me go back to something a bit maybe more physical and intuitive and talk about this classifying problem. So again, you have Eve. Eve is measuring charge, and she wants to guess the charge of the state from the measurement record. So if you believe what I just told you, you would conclude that with unlimited resources, Eve should be able to do this above the sharpening transition, because by definition, this sharpening transition is about the ability of your measurements to extract information about charge. And by unlimited resources here, I probably mean that Eve can simulate the quantum dynamics perfectly over and over again, and come up with a decoder or classifier in that way. A more practical and maybe more interesting question is whether we can do something with limited resources, like only a classical computer, and maybe we can also change the setup a little bit so that Eve has less knowledge, in which case you can come up with optimal classifiers or decoders to solve this problem. So there's one setup in which I'm going to claim we have an optimal classifier for this problem, and it's a problem where Eve doesn't have knowledge about the circuit itself. So that is to say, what Eve knows is the circuit is random. So you have Haar random gates, but she doesn't know precisely which gates were applied. Okay, so she only knows that the circuit was drawn from those random U1 gates, and she has access to the measurement record. Okay, in that setup where Eve doesn't know what the circuit is, I claim that the optimal classifier is given by this formula. And so what Eve should do is maximize this probability, which is to have a charge Q given the measurement outcomes. And this is given in terms of this small p here are Born probabilities. Okay, so this is the Born probability to observe measurement outcomes for a given circuit and an initial state with charge Q. But those Born probabilities are marginalized or sum over the circuits or the unitaries. So intuitively, what this tells you is that if Eve doesn't know the circuit, the best she can do is marginalize or sum over it. Okay. Those average Born probabilities are non-trivial because of charge conservation. So even if you marginalize over circuits, you still have very non-trivial hydrodynamic constraints because of this U1 charge. And so different charge configurations are more likely than others. And so now the question is whether we can actually compute this, and the answer is yes. It's a one-line algebra of Haar calculus to compute this average. This gives you, again, a symmetric exclusion process constrained by those measurements. And this is something we can compute those Born probabilities efficiently using a transfer matrix and TBD and matrix product states. Okay, so that's something we can do efficiently classically. So just very intuitively, what Eve is doing is as follows. So she has like measurement record. She knows, for example, there was a particle there, a charge there, and holes elsewhere. And what I'm saying is she doesn't know precisely the gates. The best she can do is just count random walks that are compatible with those measurement outcomes. So for example, you could have 2 charges compatible with those here. But of course, you could also have another charge, for example, moving there that would be compatible with those outcomes. Okay, so here, those outcomes are not enough to pin down the charge, for example, right? But so this becomes an anthropic problem. You just count random walk configurations compatible with your measurement outcomes. And I claim you can do this with TBD, and I also claim that's the best you can do here. Okay. And interestingly, this has a phase transition, which is precisely this phase transition in the large limit I told you about. So this classifier or decoder, if you want, has a success transition, which is above the sharpening transition generically, but which is in the same universality class. And so that's something we've studied in detail. So you studied the properties of that classifier, counting random walks. So very briefly, this is the probability of the correct label. So you have 2 charges. What the classifier is counting is computing is the probability of each charge. At small measurement rates, it's basically 50-50 Gaussian, whereas you crank up P, the correct label ends up having very high probability, and you pick that one. This is the entropy of the distribution of like those 2 outcomes, and it going to 0 means that you make a very confident decision. And so this is like an order parameter for this transition. So Eve can learn the chart with polynomial resources. And so this is my last slide, just to like tell you how we can go beyond this. So this is, in a simple setup where you don't know the circuits. Of course, you can ask, well, okay, what if I do know the circuits? Short of running it on a quantum computer for many, many times, what can we do while still having a simple classifier? So one simple thing you can do is use biased random walk. So for example, for each gate, you can compute this hopping probability and put this in your classifier. So say if you have a gate that happens to be very close to identity, you want to say that your particle didn't hop, almost had very little probability to hop and instead stayed in place. So that's something you can very easily put in those random walks and still simulate classically. And when we do this, we find that, that we had a threshold that was at 0.2, and we can change that threshold to 0.15 something. So we can get it lower by doing this very simple change. But the actual sharpening transition is near 0.1. So we think we can still do better here. All right, so with this, let me just very briefly conclude. I've argued there's a simpler new type of measurement-induced criticality. I say simpler, it doesn't have to do with entanglement, just like charges. It's a transition in the ability of the measurements to reveal a conserved charge inside the scrambling phase. Let me just also advertise that those stat-mech mappings are really very useful to study all those problems. They allow you to simulate things very efficiently using TBD, even though the original system is in a volume law phase. And they also allow you to use more standard tools like effective field theories. Okay. So there's a number of open questions that I'm just going to flash. And to finish, let me thank my collaborators, many of whom are in the audience, and in particular, the junior people in my group who did most of the work here. Utkarsh, who's now a postdoc here and is in the audience, and Fergus Barrett, who was a postdoc in my group. And with this, thank you very much.
Thank you very much for the talk. Questions?
Yeah, I have a very naive question. So can you see this transition just in the moments of the charge distribution?
Over trajectories, yes. Like even the variance knows about.
Yeah, then I'm surprised that you need replicas for this, because there is this story of symmetry resolved entanglement, And typically, in order to compute these moments, you don't need replicas. We can maybe discuss after.
I mean, we can discuss after. I definitely need the replicas here. Partly is, I make the measurements, and so I'm losing. Yeah, I mean, it's a nonlinear problem. Anything that's like linear in the density matrix will not see that transition. So it has the same caveats as the measurement-induced phase transition in entanglement. So, like even in that observable, say the first term, average over like unitaries is a property of the quantum channel, and this will not see the transition. It's actually the disconnected piece that sees it. So naively, you also need post-selection to see that.
Can you unmute yourself, Sam?
Hi, sorry, I didn't hear you say I could ask a question. Thanks for the talk. I had, so the first question was, since you end up with this mapping to the symmetric exclusion process in the end, would this same transition occur in a kind of completely classical setting? So, I mean, I could just take the Fokker-Planck equation for the joint probability distribution of particles evolving under SEP, and then would I see the same transition? Yeah.
Thanks. So that's a very good question, and the answer is yes. So like the model that we get, like this classical model is entirely classical. It has like positive Boltzmann weights. It is just a symmetric exclusion process, and it has all of that physics. The sharpening transition in the qubit circuit is still quantum in the sense that, like we don't have a good classical classifier that goes all the way to the sharpening transition. But if you want, the universality class of the transition is classical. That's the way I would phrase it. And the quantum corrections are irrelevant. So in that sense, it is classical.
Right, okay, thanks. And then, yeah, so the other question was kind of basic. So it was how would I understand that the sharpening time goes as log L in the sharp phase?
How do you understand? Can you repeat? Is that in entanglement?
Yeah, sorry, it was that so you have like so in the fuzzy phase, you were saying that well, so the time to sharpen should scale with the system size L.
Yeah.
And this is because if you wait for long, if your measurement rate is sufficiently low, then each time you do a measurement, it's as if you're sampling from the same probability distribution. The probability distribution of the particle positions is not recovering between your measurements. Sorry, it is recovering between your measurements. Whereas, on the other hand, if I set my measurement rate to be very, very large, I can just look at every site straight away and find that I sort of sharpen in unit time.
Okay.
So how do I understand that the corrections to
the log L
are log L? Yeah.
Yeah. So this comes from like your charge variance decays exponentially, and you want to set it equal to 1 over L, and that kind of gives you a log L from that. I can.
Right. Okay. Sure.
That makes sense. Yeah. It's because like your correlator, your charge variant decays in a timescale of order 1, but you want to get it all the way down to 1 over L, and so that gives you a log.
Right. Great. Okay. Thanks.
So I didn't understand from your answer in what way it is that the sharpening transition is quantum. In the sense, I could formulate it as a learning problem in a classical setting where my initial distribution is kind of very broad. Yes. I don't know where the charges are, and every time I measure classically, I just have more knowledge of the distribution.
Sure.
And that's
what I talked about. That's the classifier we have.
It's that's the classifier. Yes. Right. So in what sense there is quantum mechanics there? I mean, the quantum mechanics just sets up your maybe.
I'm saying, so what I want to claim is that, okay, the universality class is classical.
Yes.
Okay. And that classifier here is classical, so I can reproduce all of the same physics classically. I entirely agree about that. Yeah. If you take a qubit model and you have a sharpening transition, I would still claim, and maybe I'm wrong, but there's some quantum mechanics there, even though it's RG irrelevant, in a sense that at least we haven't managed to come up with a good classical classifier all the way.
I see.
I claim maybe you actually need a quantum computer here to do the decoding or classifying problem. And maybe that's not true.
Okay, we can discuss later. I think not. But I think the entanglement transition is still very quantum, right? Because that has, I don't know if there is a...
Yeah, I mean, it's maybe like the one over the, if you define in some way you can think that the 1/d corrections are kind of like quantumness, right? Like this largely limit maps you to something classical, percolation or like SEP here. And there's a sense in which for here 1/d corrections are irrelevant, whereas for the entanglement transition they are relevant. So maybe you can say it's more, I don't know, it's a bit, we could debate what quantum versus classical means, but I agree, you know, here definitely the we have a classical version of this. That's what the StatMech model is.
Hi, thanks for the interesting talk. Here.
Oh, yeah.
I have a question about the decodability in the charge sharp volume law phase and the area law phase, like whether there's a difference in terms of the scaling of the success rate in these two phases.
I don't think there will be. I think like once you've sharpened the phase, you've sharpened it, and here, you know, you will happen to say purify your state if it was originally mixed, but I don't know if there'll be a quantitative difference in charge here. So really they have, you know, different observables, like here you'll have charge, and I don't think anything interesting will happen with charge over here. I mean, we didn't look at it, but I cannot really imagine a reason you would have anything interesting going on in charge here.
Yeah, it sounds like there is like there's a connection to the quantum game like picture where you're trying to guess the total charge, but that sort of survives, you know, below some original critical point of the StatMech model.
Okay, maybe we can discuss, like after this you can tell me about this, and maybe there's a connection. I would say there's nothing like happening to charge here. Yeah.
Hi, I wanted to ask about one of the questions you flashed at the end. So could you comment a little bit on non-abelian charges? How much of this story would go through and what would have to change?
Yeah, I don't know if I have an answer I'm willing to like put on the record yet, but like, so yeah, so you can ask about non-abelian symmetries, and we've been thinking about coming up with, you know, similar statistical mechanics models for non-abelian symmetries. And in particular, effective field theories as well. And we have a pretty good framework that I think works, but it's hard to make, like here, like in some way, we got a little bit lucky that this transition was, like the field theory was pretty simple. The replica structure we could handle analytically. And this doesn't appear to be the case if you do like SU2 measurement-only dynamics, for example. So we're still working pretty hard on understanding this, but I can tell you about some details in private if you want.
Hi, Romain, can you comment about these higher dimensions? Do you expect some like gauge confinement, deconfinement transitions like that?
Yeah, you can think of dual versions of it. So we discussed a bit some versions of that. Let me say in higher D, like you still have this field theory that we derived kind of carries through, so you'll have like higher dimensional XY models. There is one complication. If you go away from half filling, you start generating some coupling between, let me just say a few words here. So here, like, I didn't talk too much about the action, but there's a part that's like replica symmetric that controls, if you want, the channel that controls diffusion. And we had like what we call inter-replica fluctuation, and that controls like this measurement-induced transition, and they decoupled. In higher dimension, when we go away from half filling, they start coupling in a non-trivial way. So presumably the IR fixed points is very non-trivial. So it's coupling like a z=2 mode to those relativistic modes with some relevant coupling. And so who knows what it flows to. So there are some interesting things in higher D. There's also more interesting things about boundary criticality in higher dimensions that will be relevant here.
Is there any last pressing question? If not, since we are anyway a bit over time, let's thank Romain and all the speakers.